Yeah, now it's so the next talk is from Otello Rossoni here from the this beautiful place in Rome, and he's a computational chemist. And in the last 18 years, he worked on this field, and recently he founded MaterialX, a material design company that aims to accelerate the development of new materials using the most advanced computational chemistry.
Well, thank you, Margherita, for the kind introductions, and welcome to my talk. So I will be hopefully show you how to go from the atomic level to the mesoscale and back through a multi-scale approach. So you already saw that kind of plot that shows the level of modeling. So in a multi-scale landscape, you have the highest level of theory is quantum mechanics, at least from a chemist's point of view. As we increase the length, the time scale, and the system size, we have to use different kind of approximations. So we go, so if we neglect the electronic structure, we go into the realm of molecular dynamics. So just to give you a scale, the most advanced DFT, linear scaling DFT methods allow you to study up to something like 10,000 atoms. But if you want to model 10,000 molecules, you definitely need to get the electronic structure and use molecular dynamics. With molecular dynamics, you can go up to the microsecond time scale if your pockets are really deep, like if you do drug discovery. But otherwise, if you want to reach, let's say, the size of microns, you have to use some sort of coarse graining. So we forget the atomic structure and we model an entire molecule with a coarse representation. And we can also use this level of description to model a representative volume element on a complex system and use this information in finite element methods that are, we enter the realm of computational engineering. So the MaterialX uses the MOLC model, which is a coarse grain model which I have developed with my colleagues in Bologna. So a coarse grain method, as I said, is a way of representing a molecule with a coarser representation. So in this example, this is an organic semiconductor. This molecule has 78 atoms, and we use, 5 ellipsoids to represent the shape of the molecule. And what you see here is the basic expression of the force field. So the interactions used to describe how these coarse grain objects interact. So we have the first two terms in this summation represent the intermolecular interactions. So we have a gay-Bern potential, which is nothing more than a Lennard-Jones potential, but generalized for spheroids. And to give you a sense, it describes the stickiness of molecules as they approach close to each other. And the second term is a classic Coulomb summation. So for the electrostatic interactions, which is also an important part. And then we have an intramolecular term. So it's an effective two-body potential connecting every two connected pairs of ellipsoids. And it depends on the radius connecting the two beads, plus the orientation of the two objects, so which are expressed as the quaternions Q1 and Q2. So this MOLC model is parameterized from the bottom up, so you do not need any experimental knowledge of your system to be able to describe it. So in this example, I show you the highest occupied orbital of pyridine. Of course, it is computed at the quantum mechanical level. There's a number of information we can extract from the wave function, but a very important one is the square of it, so describing the electron density around the molecule. And from that, we can compute the molecular electrostatic potential which is very important for good solid state properties. So in the next step, we have this potential, and from that, we can fit a coarse grain potential with a number of charges inside an ellipsoid, and that would be our coarse grain model. So to recap, this MLC model is based on spheroids that are connected by directional bonds, allowing for some degrees of flexibility. The shape of the molecule, so the excluded volume, is very well reproduced. So in turn, we get very good densities and radial distribution functions. And I will demonstrate that later. Then we have these two terms, so for intermolecular interactions. So we can balance the ratio between electrostatic interactions and dispersive interactions, and therefore we can get very accurate formation enthalpies and transition temperatures at the coarse grain level. And most importantly, we have a one-to-one mapping procedure, which means we can reverse map the coarse grain structure, the atomic structure, without losing information. And now I'm going to show you how to do a multi-scale simulation in practice. So here you can see a classic molecular dynamics simulation. So all the atoms are moving. What we are interested here is to represent the overall shape of the molecule at the coarse grain level. So we freeze relatively rigid sections of the molecules and we replace them with ellipsoid. As I said, they are connected with a two-body potential, allowing for flexibility. So it controls the position and relative orientation. And since we have good intermolecular interactions, we can have good solid state properties. So in this example, I use that molecule to create an amorphous sample of this semiconductor, and its density agrees with the experimental one. And most importantly, we can reverse map this structure to the atomic structure. So go one level down in the multi-scale approach and continue with a classic molecular dynamics simulation, and as you can see in this most transition. And then we can eventually pick up some molecules of interest and run DFT calculations on top of that, for instance. So that's what we did in this work in collaboration with Gabriele Davino at Institut Néel in Grenoble. So we studied two organic semiconductors. You see the chemical structure of sparotag and TCTA. And you see also the coarse grain structure superimposed with atomic structure. Then there is a dopant molecule, which is F6 TCNNQ. Just to, so structural properties are fine, but here what I'm interested to show are the density of states of holes and electrons in these materials, both for the semiconductor and the dopant molecules. So on the top panel, the pristine materials, and then two dope samples. Well, physically, you see that the energy level of the dopants and the host overlap when the system is ionized. But the interesting thing is that we have, so the thin lines are the reference calculations done with all atom molecular dynamics simulations, while the thick lines are from the multi-scale approach. So we start from a coarse grain structure, and then we reverse map to the atomic structure and finally run the electronic structure calculations. And as you can see, the density of states agree pretty well. Now, here we are interested in battery optimization, and of course, computational material science offers a fresh view into these complex materials, as Michael shown in the previous talk. And here I have highlighted four aspects that can be that can benefit from multi-scale simulation. So first of all, we have electrolyte transfer simulation. So compute the diffusivity of species on both solid or liquid electrolytes And then we have the formation of the solid electrolyte interface layer. Then an example of an active material morphology. So we can, so this sample in particular is 60 nanometers cube. And we can have a fractal geometry and explore complex shapes. Another important effect is that these materials undergo significant stress upon charging and discharging. So we can use the information simulated in the mesoscale to allow for ambient effect in these materials. So stress and aging related to these cycles of compression and deformation of the materials. So for the diffusion coefficients here, I'll show you the self-diffusion coefficients of 6 organic solvents simulated with the coarse grain method. So you see that structure here, and we compare NPT simulations, so constant temperature and pressure, and the atomistic simulations typically use an integrator of 2 femtosecond. For the coarse grain simulations, we use the time step of 10 femtoseconds. So you see on the right and left-hand side panel, the comparison between the density in the x-axis computed with atomistic simulations, on the y-axis, the coarse grain simulations. And I have 2 series of data. So the triangles would be the coarse grain model, so the MOLC, while the circles are rigid molecules. So they are fully atomistic molecules, but just kept rigid, just to give you a sense of how something with a similar shape, but a fully atomistic resolution behave when we just freeze it. And as you can see for the densities, the 2 different models are basically almost identical. And on the bottom panel, you see the self-diffusion coefficient, and also, well, that's a bit more variation, but we are on the same order of magnitude. So we have just few, I mean, something around 10% error between the coarse grain model and the atomistic model, which is a very good result indeed for this kind of models. And the other panels show the radial distribution functions of the liquids. So they describe how the molecules, so what's the probability of finding a molecule, starting counting from any molecule in the liquid. And so the height tells you how many molecules there are at a certain level, at a certain distance. And so they're basically the coordination shells in the liquid. And as you can see, the reference is the dashed red line, while the black one is the coarse grain result. Right, then if we want to study a solid electrolyte, you also need to be able to reproduce the condensed phase, and for some materials also the crystal phase. And there's something really tough to do with coarse grain models. Here I'll show you 3 materials that are hexadiaphene, tryptyrene, which is a lipid, and P3HT, which is a polymer. And you see the comparison between the experimental and reference atomistic simulation and the coarse grain model. And I have to say, I was pretty impressed by that kind of agreement, especially for densities and overall the shape of the unit cell. Then, of course, we can scale up, and interfaces are really important in battery design. So in this example, I'll show you a surface of a polymer. The unit cell would be the box you see in the center, and the green layer is a solvent, the MSO. And so we can also model things like wettability, adhesion energies, surface tension, that kind of stuff. So this cutout you see is a detail, is the top view of the surface. This particular one is plane on. and that's a configuration that can be created experimentally. And we have also an atomic force microscopy image of the same material on the same scale. And as you can see, there's a very good agreement. So if you count the same number of chains in that sample. So just to conclude, the MOLC is our force field to run coarse-grained simulations, which are part of this multi-scale approach. It's based on spheroids, and it includes short and long-range interactions plus directional bonds. And the most important feature is that it allows a seamless conversion between the coarse grain and atomistic coordinates. And I would say that multi-scale simulations are really critical if you want to address problems such as I don't know, grain boundaries or defects on interfaces. You really need to model these systems at a larger scale. So it's not enough just to have a small sample representing that kind of system. And I'd also like to acknowledge my friends and collaborator, Matteo Ricci, for coding this part, and Andrew Jewett, which is the author of Moltemplate, for supporting our model into his program, which is a scripting language to create complex input files for molecular dynamics simulation. And all the references of the work shown can be found on the company's website, which is materialx.co.uk. So thank you for your kind attention, and open to questions.
Thank you, Tello. This was really clear, interesting talk. And let's see if there are questions from the audience. Yeah, please. Oh, okay. Oh, no. So this is all modeling systems that exist, or some particular material that has these particular components, and it's modeling what happens. But can it be used the other way around if you want to to predict something? So if you want a particular interaction, can you then go and build a material from different elements, say, of different molecules, to have that kind of interaction? So can you go the other way around, not just modeling systems that exist, but predicting particular behaviors? So if I want a material to do something, can I use this to build it?
Yes, yes, that's exactly. I mean, if you think about it, that's exactly what you do if you are a material scientist and you have something in mind. You design, like, if you want to introduce some kind of directionality in the bonds or in the interaction of system, you may think, okay, I may modify the chemical structure of a polymer, introducing, I don't know, a carbonyl group somewhere to strengthen or to give, like, to increase the order of the material. So you may have this idea, and as Michele said, so far the only way to test these ideas was to, well, actually make the material, purify it, and make devices and make measurements on that. So you can indeed use computational material science to build a molecule without synthesizing it, and use the predictions as a well, to probe what are the properties. Then there are other things that may pop out, like you may screw up like the shape of the molecule. So because you can change the chemical structure, so like the structure of the starting material, make some modification and say, oh, I expect to have that kind of change. Then discover something else in the simulations. Is that something like, or two groups that were small enough to be close to each other now are a bit bigger. So that creates so screw up the balance of forces in the like in the packing of the material, and then something else changes. But all of that can be, if you have a good model with like you trust it's been calibrated, it has been tested in known systems. Once you reach that level of confidence, you can indeed use simulations to like verify that your idea actually creates the modification you have in mind.
Thank you. Very interesting.
Hope that answered the question.
Are there any other questions from remote audience? We cannot see them.
May I have a brief question? I'm Giancarlo Cappellini.
Yeah, please.
From remote.
Yeah.
Yes, first of all, compliments for the very nice talk. And the second point was a simple question. Is your method could be used, your method, even for other scenarios, just like, for example, for docking in the case of drug delivery? And if yes, what are your experience about that? Just because in some sense, I think you could be very predictive, sorry, with your method in such questions.
Yeah, that's a very good point. It's yeah, indeed, it's let's say the parameterization of the MOLC model is general, so it can indeed be used, can be used to model like diffusion across membranes or and in fact, I mean, you see tristearine in the crystal structure prediction. That was indeed work I'm doing for drug delivery. So this is not my area of expertise. So I've never done drug discovery or biophysics simulations before, but I'm exploring this sector with a colleague at the University of West of England, and we are modeling the cellular membranes. So we are validating the model for membranes, and then we will run simulations to see the diffusivity across membranes of selected species. And in perspective, that could be part of a, let's say, a multi-scale approach for drugs, to test the efficacy of drug delivery. Yeah.
Okay, thanks. And the other fact is, you can even study, for example, small molecules, biomolecules on solid surfaces with your method, which would be very useful to begin to study such problem. And then after you have your first results, try to use other approaches, for example, ab initio ones. Could be very interesting in this case.
Yes, and I have to say, what I have verified so far is that if you want to run DFT calculation, I mean ab initio calculations from a coarse grain model, you can really directly reverse map the atomic structure, the extended system at the coarse grain level, because it includes electrostatic interactions, and those are important to put them directly into the ab initio calculations, and then run your calculation, and you will have a good input system with, I mean, a realistic geometry. I mean, not like you are in a saddle point or very weird unphysical like bonds and angles. So it's pretty accurate with organic semiconductors doping. But as I said, I'm not an expert in biomolecules, but I mean, I see no reason why it wouldn't work. Systems too.
Very interesting. Thank you so much. Thank you so much.
Thank you. We are running time, so we